Today's topic is related to masonry design, and I will show you new possibilities that were implemented within 2023 version of Advanced Design that extends the possibility for a design according to Eurocode and other national standards related to masonry design. My name is Kamil Dziedzic and I'm a solution technical specialist at GRAITEC Poland. I'm responsible for structural softwares. I'm a structural engineer myself. Before we start, in a few words, what is GRAITEC Advanced Design? As you may know, it's a finite element solution dedicated to structural design purposes. It allows for very intuitive work with easy modeling, loading, and performing many different kind of analysis using finite element method. After you've done your static calculation analysis, you can design concrete, timber, steel, and starting with new version also masonry elements using national annexes to Eurocode or North American codes. What's most important, it's a BIM compliant solution, so you can connect it, link it with Revit, with Advanced Steel, but also any other software using open formats such as EFC. And now about a new masonry design module. It's a brand new tool that is fully implemented within Advanced Design, but it allows you for many different work scenarios. What's most important is that it can be used directly within your finite element model. So as soon as you calculate, as soon as you've done the static analysis of your global finite element method model, you can run the design calculation using Eurocode with national annexes to design a particular masonry wall. But also it can be run as fully standalone separated application where an user fully defines all the geometry, material, loads for a single wall and can perform and design separately without even caring about performing finite element method analysis. I will try to show you those two different approaches, these two different scenarios during this webinar, and we will see what are the differences and what are the benefits of using both scenarios. As you can see, using this new masonry design module, you can design not only very simple single leaf walls, but also more complex walls if it comes to its structure. For example, cavity walls, double leaf walls, and so on. And also you can mix a variety of unit material. So not only clay, but also aerated concrete, silicates, and so on. What's most important is that you don't design a single particular panel at once, but you design a whole wall that consists many panels which were defined by the openings within your wall. Also, we perform any checks that are requested by Eurocode or any other standard that was implemented. So vertical loading, shear loading, bending, stresses, and so on. As I previously mentioned, I will show two approaches to the design with new masonry module. So the one when we use our global finite element method model, and we run the analysis for all the model and we pick a particular wall and design using previously obtained results. And for this, I will show you how to introduce a masonry material in your finite element model and how to correctly define a wall in Advanced Design 2023. Then we will run a design calculation for these masonry walls. And what's most important there is how we take the finite element results to obtain a design forces for particular panels. Then we will jump to standalone application for a module where I will show you how to quickly define a wall, how to specify all the assumption and loadings. And so you can see that even though you don't have a very complex finite element method model, you can run very detailed calculation of a single wall. So starting with advanced design, in order to perform a design of masonry walls within that system, we've needed to introduce a new material family. So in addition to the current ones like concrete, steel, or timber, you got a new family called masonry, where you can specify not only the mechanic properties, but also strength parameters according to the standards you're working on. So we made this approach the most simple way. So you just create a new material where you specify a unit and also a motor, and basing on these two inputs, in the most simple form, let's say for a single leaf wall, you get all the characteristic calculated automatically. So the strength is calculated according to a Eurocode, and the stiffness is assumed basing on the strength parameters. In the FEM analysis, it's also very simple because you use standard planar element modeled as a shell type with this new masonry material assigned to this element. What's new comparing to other design sequences for other elements is how we obtain a design forces, because a new strip method was implemented for this course. So let's now jump into advanced design and see how it's done in practice. So first thing to notice when you are in advanced design already is that on the configuration tab, standards, you have a new entry for masonry where you can pick one of three standards for masonry design: Eurocode 6, Italian NTC, and Romanian CES6. For Eurocode 6, as you can notice, there are several national appendings. So starting with the general one, so the basic general rules without any national annexes. But you can also pick Czech Republic, France, Poland, Romania, Slovakia, and the United Kingdom, and also starting with 2023.1, Portugal, Spain, and Germany. So basically, most of the Europe is already covered. So for this webinar, I will stick just to the general rules, and I'll hit OK. Okay, so we'll right now open a model. I will start with an existing one that I prepared before, and we'll see how are the masonry walls defined, and what's most important, how is the masonry material in this project defined. So basically, whenever you start a new design, you need to provide some structural elements such as beam, columns, slabs, and walls. And usually you assign some material to these entities. But if it comes to masonry materials, you need to prepare them. Let's check Manage tab and Use Materials library. Because for steel, concrete, and timber, you got all the materials directly defined within the library, but for masonry materials, there is only one entry with some default settings. Let's say it's a single leaf wall. At this moment, I don't even know what are the units, what are the mortars. Why so? Because masonry wall can be mix of many different units like clay, concrete, aerated concrete blocks and so on. They can be of different dimension, different thickness. We can use many different mortar types. So each time you will introduce a new section, you simply need to specify the units. So I will add, just as an example, a new material. I will say it's a silicate blocks. I can, this is just a name, this is just a tag. I can say what class, for example, 15. I can say the thickness, just so I'm sure what material I'll be using when I assign it to any element. Okay, we will need to change the family type of this material to Masonry, and as you can see, the standard is what we already selected in the configuration dialog. So it's just Eurocode 6 general. And this material has its own properties related to the code. So as you can see, I got unit, mortar, and thickness, and these three are most crucial, most important parameters. You can also have some additional settings. How are the joints field, if the leaf is bearing or not, and so on. But as you can see, according to the specified unit and mortar, all the strength parameters are calculated automatically. The mechanical properties are also calculated automatically basing on these strength parameters. So right now I can simply specify a block. Right now I have mix of many different databases. Some of the Polish blocks, some of just general. Let's say I will pick a block as specified in the name. So let's say it's a full solid silicate block of class 15. So its compressive strength it's 15 megapascals. And I will pick some mortar. It could be thin layer. It could be general purpose. As you can see, for silicate blocks, as it's stated in the Eurocode, we cannot use light mortar. So let's say it will be general purpose mortar of 10 class if it comes to strength. I can also specify a thickness. It's a new approach in comparison to other materials because we usually had a material and the thickness was related to certain element. If it comes to masonry material, it's done different, however, because it's related to a specific block. And also, as you can see, you can use many different wall types. So it can be single leaf, it can be double leaf, it can be cavity, and so on. And the mechanical properties are steered with the thickness. So if you have different leaves with different blocks, so example, one is silicate and the other is clay, the stiffness of this wall will be some average between these two, and it's steered with the thickness for bending, thickness for bearing, in comparison to the total thickness, which is a sum of all leaves. Also, some leaves might not be bearing for vertical loads, and some of the leaves might not be bearing for bending. Let's say the cavity leaves are not connected together with ties, so only the outer leaf will can be resistant to bending. Right now I will just leave it as a single leaf wall. And so as you can see right now, mechanical properties are calculated accordingly. I specified much stronger blocks and the longitudinal rigidity increased. As usual, because it's just a material properties for your calculation using finite element method, you can also change behavior from isotropic to autotropic. In most cases for masonry walls, we could introduce some reduction to the scale of rigidity for this G to 1 direction, usually about 80 to 90% of reduction. But this time I will just leave it as isotropic, so it has the same values in both main directions, so according to x and y local axis. Okay, so right now all you have to do is to assign materials to planar elements. We will model our masonry walls just as we modeled any other wall, any other planar element. So simply going with a planar element, and all we have to change is a material. So I prepared a new silicate blocks defined previously. So as you can see right now, I'm presenting the color of element by material. So as you can see, it's a new silicate block. Of course, I can change the color to see better, to distinguish better my materials provided in the model. Let's say I will right now stick to something else than black. If it comes to modeling of masonry walls, what we'll have to design is actually some panels. So usually between the openings, we will design each panel separately. But you don't have to divide the element to make them separate, so you can design them separately. Actually, what you would like to do is to leave it as its full solid element, because our design module will distinguish each panel and it will be designed on calculated design force using strip method. So for each panel, we will have a strip, separate strip, in which we will integrate our efforts. Soon I will show you how it's done. But right now, please notice that the thickness of the element is grayed out, so it's always defined with the material. If the material changes, so for example, I got our material and for some reason it had to be increased to some different value, as you can see, the thickness of the element that had this material used will also increase. And it of course makes sense, as the thickness comes usually from the dimension of particular blocks that we will use. Okay, I can change some of the previously defined walls that also been of the silicate class to our new introduced materials, and I will just run the finite element calculation. So right now we have solved a static calculation for 3 simple cases and some of the static linear static combinations. I will hide the mesh and we can browse some results. As usually, we can go with displacement forces and stresses and also resultant forces. But what will be used for actual masonry design are simply just forces. So we go with planar element forces. Okay, let's see. I will just isolate masonry elements from this model. I will filter the view just to see the masonry elements. Please see that if it comes to the forces, we can display them as usual for any other planar element. So according to local x and y axis, I will maybe show this using envelopes. So in this particular model, my x-force is a horizontal one and y-force is a vertical one. However, it's usually hard to tell for user how are the forces changing in the particular element. So what will be the force assumed to the design? If it will be max of this, if it will be minimum, if it will be the average. I will switch right now display mode from isomaps to diagrams. So I will show the distribution of vertical force with vertical diagrams. So as you can see, all of this wall is at this moment fully in compression. And because we have all the graphs on the one side of the element. As you can see, it's not evenly, even though it's nearly, but it's not evenly compressed. Some of the part of walls, let's call them our panels, are more compressed than the others, but some of them are not as long as the other ones. And if we will check any other wall, so as you can see, this external panel is most compressed in comparison to some other ones. Why so? It's because of the solution that we have used, which is finite element method. So the stiffness, the global stiffness of this model is taken into account. So if we have any more stiffened element than this particular wall, for example, here I have a concrete walls, probably take all the loadings instead of this part of my masonry wall. So the internal forces right now are basis of our design. But as I said, the design forces that we will finally use are calculated using strip method. At this moment, we can't see what will be done because we need to provide some strips. But what's most important is that automatically, on default, the strips are assumed between the openings. So each panel you will have between opening will be calculated on this integrated effort. Let's now see how it's done within the module. So in order to design a masonry wall, we'll need to open it with the design module. But notice you can also export it because the modules are run also as a standalone application. So you can export it for your colleague who will design the masonry walls, or you can export it for yourself or to just work with the standalone version of this application. But right now I will just open it, so it will be fully integrated within this module. So as you can see, I have my wall with the exact dimensions, with the exact material parameters as it was on the global model. I can hide the dimensions because it's not necessary for me to see. I can also hide the views and leave only the main view where I see all my design panels. As you can see, some are in blue and some are in gray. The one with the blue numbering are the one dimensioned, and the one with the gray numbering are the ones that are not designed actually, but the force is distributed to the neighboring designed panels. So at this moment, the data about geometry and material is not the only thing imported. Also, you can see that the FEM results are here as well. In each case, in each combination, you can display FEM efforts as it was done in the analysis view. But as you can notice here, for each separate panel, we now have generated strip. You can manipulate the width of the strip if it's necessary, but in this case, I would say we can stick to this one that are generated automatically. So in most cases, user doesn't have to do anything with the strips. For these strips, we have integrated the efforts that we can see right now on screen. So the integrated effort is our design force separately for each panel. So right now I'm displaying vertical force in a simple case, and I can switch to some combination. As you can see, some strips and some panels are more compressed in comparison to the other. Right now I have set that when I highlight a particular strip, you can see how the forces were integrated. Please notice that also the part from the lintel is also integrated in the design effort for this particular panel. Right now, what you can do, in addition to section and integrating force, is to simply set design assumptions. You can pick between two methods introduced with Eurocode, so the first part of Eurocode 6 or third part of Eurocode 6 introduce different method, one which is more complex and one which is simplified but very restricted. You can also specify verification which you will like to perform. So maybe in some cases vertical loads are enough, but we can leave all of the verification selected. If there are no checks to perform, like for example concentrated loadings or bending at this moment, we will simply not run the verification. The partial factors are fully calculated automatically according to selected annex. So right now we will need to specify execution control and the motor preparation type, which I will leave right now as default. Please note that the wall section is as defined in your model. You can also modify it here and update within your model if necessary. In addition, you also have some geometry settings which might be necessary to define for simplify method when we base on the geometry of a wall. How is the wall restrained and how is the wall supported by other elements. But for this detailed method, I will leave it as it was imported. And right now I can run the calculations. As you can see, in the info panel you can browse the results quickly for all the checks that were performed. So the vertical loads, shear in plane and shear out of plane. Please note that at this moment we can see the most decisive, the critical panel, which is panel 16, but the verification were run for all the panels that were defined within this wall. So for example, you can browse the results for panel 3, you can browse the results for panel 14, and so on. Then you can switch to any other wall and run the calculations of all the panels that were included in that wall. Now let's see another solution, another approach to design of masonry wall. As you could see previously, we can fully design planar elements, which are our masonry walls that are modeled within our FEM model. But you may or you might not know that the module can run fully on its own. So it can be run as a standalone application where you do all the modeling and the design for a single wall. So right now I would like to show you the workflow and how it's done, what are some assumptions needed to consider to correctly and quickly, most important, to quickly design masonry wall using this module. So as you can see right now, I'm in the module and the possibilities are limited only to design of masonry walls. But if it comes to the design, you have the exact same possibilities allowed by Eurocode 6 that you could see in advanced design. The difference is that the internal forces obtained analytically, not using any numerical method, and also you work on a separated individual entities such as single wall or even single panel. So for each wall, you need to prepare individual model. Right now, you can start a new file, new project, or you can use some predefined types. Even if you start with one of these, you can change the settings, the localization as you are already in that file. So let's say I will start with some intermediate floor internal wall, and I hit OK. So right now, as you can see, we have a single wall and it has some dimensions that can be modified by user. So let's say I will start with that. You can either use the dimension lines you can see in the viewports. So you work with 3 dedicated viewports that you can switch to any second. Or you can jump to the geometry dialog. Here you will find the exact same dimensions, for example, level height or wall length, but also some more specific settings. For example, wall system type and location type. It means if the wall is internal, external, and on which floor it's located. It will be related to some checks according to the Eurocode. Most importantly in the simplified method, where the geometry of the wall has great impact on the reduction factor. But also on loading. Right now we don't use FEM numerical methods to calculate internal forces. We will use the geometry of the wall to assume the internal forces according to the provided loads. So right now we will leave it as it is. So it's internal wall of the interstory. You can also add openings. So right now it's just a single design panel, but you can add as many openings as it's required for this wall. You can simply draw them or again use dimension lines. So right now when I added them, I can see dimension lines that I could use to modify the openings. Let's say I will do it like this. And please notice that at this moment, it's very similar to what we we've seen on advanced design. You have 3 design panels and also some that are not considered in the design, but the efforts are distributed to the neighboring panels. In advanced design, it was done using strips. So we integrated internal PEM forces into the integrated resultant forces. But right now, we will simply just take the loading and distribute it on 3 design panels. So let's see about the geometry. We have wall geometry and openings right now, which you can delete or modify using the dialog, as we did with the dimension lines. Let's now add upper elements, which are our upper slab or crown beam. The geometry of these elements will lead to different bending moment calculations from coming slabs. Also, self-weight of these elements will be included in the internal forces. So let's say it will be slab on both sides as its internal wall of a certain thickness, but also the slabs, as you can see on 3D view right now, could have different lengths, resulting in different bending moments coming from one side. The end support of this slab might be fixed, pinned on free, and it will also lead to different load distribution, but also to different bending moments calculated according to Annex C. So please see I done this like this, so different span lengths on each floor with some different end supports. But also, in addition to support conditions of a slab, you also have a support condition of your wall. What these settings will lead to? Most importantly, different calculation of bending moment in plane of a wall. So we will consider 2 planes of failure, perpendicular and parallel to bed joints. I will leave all the edges pinned. Also, I could say how is this wall restrained vertically in order to calculate reduction factor for effective height. In additional settings, you also have this possibility to set the depth of supports for slabs, but as our slab is continuous, this setting has nothing to do in this particular case. The design assumptions are very limited. It's as we saw on advanced design. You can choose the method with which you will design your masonry wall. So we will leave this as detailed, meaning we will calculate bending moments using Annex C and first part of Eurocode 6. Simplified method based simply on geometry. So we only assume the reduction factor for strength, for resistance, considering the geometry of the wall. Partial factors, as before, we will leave as automatically calculated according to material and class of execution. Let's see a wall section. This is what we did on advanced design in order to model a planar element with masonry material. But here, we simply need it for the design. So you can again set the section type as it was on advanced design, and each leaf has its masonry unit. The units are exactly the same as we've seen before. So this time, let's say I will go with aerated concrete on thin layer mortar. Wall section database, Masonry units, and Mota are simply free databases that will help you solve next projects. In Masonry units, you can add or modify or use any other database of the units provided by producer or by you. If it comes to wall section database, you can add a predefined wall sections to be used in next project. If you use many times very similar or exactly the same wall sections with the exact same unit, same mortar and same thickness, you can add it to not do this each time. So that's it if it comes to geometry. So comparing this to advanced design, it's just as you have modeled the wall with openings in your PEM model. So you might have many stories, many different walls, and right now we've only taken one of them, modeled the exact geometry of it, and provided some assumption, the geometry assumptions. Right now what's left are the loads. So you have again load cases, which you can add. But right now, please see that the self-weight of slabs and this wall is included in the first dead load case. Right now, I will just leave two loads, dead loads and live loads. But for the loads, you have many different types because some of the loads will be considered for different checks. For example, concentrated loads will be included both in the vertical verification, vertical resistance verification, but also we will check the concentrated load verification. For example, if it comes to the loads coming from slabs, we will also include them in the vertical loads verification, but they will provide some additional bending moment coming from the slabs. So it will lead to a reduction of vertical capacity. If it comes to planar loads, we have two different types. So for example, the parallel to face of a wall, which will again be included in vertical verification. But also you have perpendicular loads. So for example, wind or some pressure to the wall that we will calculate bending of a wall with. The internal efforts can be used, but it's not the, let's say, not the expected scenario, because internal loads are just values of design efforts in each panel provided by user, which might be also imported from advanced design. So this is a case where we use our FEM model. So right now I will provide some loadings, but please note that you can provide as many loads as you wish, and all the verification will be performed simultaneously. So let's say I will start with concentrated load. So it can be any value at any APSICA. And here we have the load width, load depth, so the depth of support to the wall, and the coordinate. So how high is the load provided on. So this will be related to the height of the beam. But also you can provide any more loadings in many different cases on many other APSICAs. So the check will be performed on each of it. Let's also add a load coming from the next stories. So from the upper story, we'll provide some vertical loading. And also I will add some loads on the slab. Right now, just as an example, so I don't need to add exactly on the all slabs. And also the perpendicular planar load, just to see if the verification will be performed alongside with the vertical ones. So right now the loads are added, and you simply hit calculate and you get all the results. So right now I see that the actual capacity has been exceeded in some panel, but please note that we checked not only one or most affected panel, we made the checks for all of the pre-designed panels. In the calculation results, you can see the exact performed verification. So for example, for the concentrated load, the most deciding is the one at third meta, Psica. The shear load out of plane with this perpendicular load, it's fulfilled. And we also checked the bending moment resistance in two planes. But the vertical loads, they are sum of many different loadings coming from the upper story, coming from slabs, coming from the concentrated loads. And for these checks, it's not enough. So as we see, we can check first panel, third panel, and fourth panel. So as you can see, all didn't pass. So we can modify the geometry, or you can modify the wall section. For example, we could go with a different masonry unit of bigger compressive strength. I could also provide a different block of a different thickness. So as you can see, the modification is very easy to do and to perform the check. So right now I simply calculated with different geometry settings. So I simply modified wall section, but you can also modify the geometry of openings, geometry of wall. You can modify loads and assumptions. So let's say if I modify it like this, my most decisive affected panel is of course panel 1. But if I move this opening a little bit, and this time the third one is the most decisive one because of the concentrated loading that we have on this third panel. But this summary table is not all that we can see about the design checks. As for any other module that we have, you can also see some more complex results. In addition to Eurocode checks that are required by the Eurocode, we have also stress check. So it's classical mechanical check of the stresses and the limit stress. But what's most important, you can generate a design report. As you can see in settings, we have two levels of detail if it comes to the reports. We got detailed report and the synthetic report. So this is just a summary, pretty comparable to the table that we've seen. But the detailed report contains all the checks with the equations and are explained where are the values coming from. So right now I will just hit OK with the detailed report, and I can either preview it or generate it to some printable format. So please see right now that we have very detailed report generated right now with 17 pages. And this could be either for you to check how was the design performed, or you can deliver it as a design report. So please see, you can see all the assumptions. So the geometry description with all the design panels, material, so the section of a wall, how it's structured, what is the masonry unit, what are the thickness, again the loads, and then it's followed by design assumption. So assumptions according to Eurocode. Then we perform each check with very descriptive results. So you can see all the equations and the values, and also a point from Eurocode from which this equation is coming from. You can generate the report after each calculation, so you can even compare the differences that are coming from two different calculations done by you. So that's it for today. Thank you for your attending to this webinar, to this presentation. I hope you like this brief introduction to Masonry module. If you have any questions, please input them in the chat in the console that you can see on the screen. I will try to